Hello everyone. In this video I'm going to show you how to calculate a lift and drag coefficients, lift force and drag coefficients in ANSYS Fluent. First I'm going to use Design Modeler to create a geometry, something like a truck, commercial trucks. Then based on that I will calculate the drag forces and drag coefficient and lift forces. So here I will go to XY plane, create a new sketch. I will keep the units as meters. So here I will go to sketching. I will zoom a little bit. So I will create a rectangular. Okay, so the body I'm going to create is 2.5 meters in length, 0.32 in width, and 0.46 in height. So I will use the dimensions, general, that's defined as 2.5, and for the height I have 0.46. 0.46, and here to have a I will create a fillet, so the radius should be lower. Let's try 0.2. Okay, so I will create a little bit aerodynamic shape in the front. So I will go to modeling, sketch, extrude, sketch, and direction. I will do the symmetric direction, so we have the width of 0.32, so each side will be 0.16. So I will put 0.16 here, so it will go 0.16 to each side. So I will press generate. Now we have our truck body. The next step is to create an enclosure. So I will, as a airfield. So I will create an enclosure. So for the enclosure, I will use 0.16 meters in length, which means that 8 meters, 16 meters in length, which means 8 meters in each side. So in X direction, I will put 8. And in minus X direction I will put 8. For height is 2.2, which means that's 1.1 in each direction. 1.1, 1.1, then and in the width 1.5, which means in Z direction. 0.5 here, 1.5 here. So I will press generate. So this is the enclosure, or something like a wind tunnel we are going to test on this like almost truck shaped body. So here we can go to meshing and Fluent, use both of these bodies, but since we don't need the body of the truck, we don't want to calculate the heat transfer coefficient, so I will go and subtract this truck body from the air, so because I only need the shape of the truck in the air. So I will go and create a boolean and subtract. So the target body is this one, the tool body is truck, and I don't need to keep the tool body or truck. So I will subtract this one, so I will have one body as the air. So I will close the Design Modeler and open the meshing. So I will go ahead and open the meshing. So in this tutorial I'm using the ANSYS meshing, but in the newer versions the Fluent meshing is very powerful and it has very nice tools. So I will try to post some videos about the how to use the Fluent meshing, and you will see how effective and easy is the Fluent meshing these days in the newer version. So here I will create some inflations or boundary mesh layers on this truck body. So I will go and insert, I will select inflation. So the geometry, I will select the body as this one, and for the boundary I need to select the whole truck bodies. I will press Ctrl A, so it will select all of the surfaces, and like holding down the control I will deselect the enclosures outer walls, or so I'll deselect all of these 6 bodies, and I have selected this truck body walls. So I will go ahead and apply. So I want to have 10 layers of inflation layers around the truck to capture as much as I can the vorticity turbulences, and then I will go for the sizing. I want to have the maximum size of 0.5 meter, and so this one should be smaller than that 1.2. For the element size I will generate the mesh to see what it looks like. Okay, we have our mesh here. Let's create a section plane, cut through the mesh to see how it looks like. You can see that it has nice layers around the truck body, and we have a that mesh. So I will select this one, and I want to see the quality. I want to see how is the skewness. So the skewness is less than 0.83, so it looks okay to me. For this calculation it should be as low as possible. For this calculation it's okay. So it's also common to check the orthogonal quality, but I will convert the mesh in Fluent, so we don't need to worry about that one. So front side of the truck is the inlet, so I will define this one as name selection. The shortcut is N, so inlet, and I will define this side as outlet. Press N, outlet. So I will select these and define as walls, and also I will select all, deselect these, to define a name selection for the truck body. Press N and name it truck. Then I will go ahead and update the mesh, so it will send the mesh to the Fluent. So I will minimize this meshing, open Fluent. So I will use parallel. I have 8 CPUs. I'm using the Intel CPUs, and I have installed the Intel MPI on this machine, so I will select this one. Now we have the Fluent open, so the first thing I will do, convert our mesh to polyhedral, which has a better convergence quality and faster Fluent So okay, it's done, and suggest to reorder our partitions as in the parallel solving after converting the mesh. So I will run these commands. Okay, it's done. So I will use the SSD K omega turbulence model. And material, we need only air. So I will, for the cell zone, which is the fluid, we have one single cell zone, so which is air. So I will leave this one as is. So for the inlet, I will define the 60 meter per second of the airflow from the inlet, and I will leave the outlet as a pressure outlet, and I will not touch the walls. So I will go ahead and close this boundary condition. So for the to calculate the drag coefficient, we will go to the report definition, new force report drag. So in this window, I will name this one as drag coefficient. So this is the force vector in which direction you want to calculate the drag force. In our case, this is in x direction because we have the airflow in the x direction. So I will keep this one as 1, 0, 0. So I want to report to a file and plot this one. The surface I want to calculate is the truck, as I selected and defined the name selection in the meshing. So I will click OK. Also, we need to calculate the lift force to see what's the lift force. So I will go to lift force. So this is the lift coefficient on truck, and the direction is y. So because lift is in the y direction for this case, so I want to report to the file and plot and press OK. So we are done with our reports. So also I want to I will run first, then do the counters. So I will initialize. Okay. I want to do the 200 time steps or 200 iterations to see if it will reach the convergence. As it solves the problem, it will calculate the lift and drag force coefficients in each iteration. So I will pause the video, and when it's converged, I will continue. So now our solution is converged. It didn't converge at 200 times iterations, so I pressed to calculate again in 226. The solution was converged. So I will go ahead, and as you can see, we have a error in the drag coefficient at the beginning, then but it kind of converged to a constant number. So let's plot the velocity. So I will define a plane in XY, an XY plane, so I can put any arbitrary number here. Just put the z's as 0, 1, 13. I will create this plane number 4. On the plane number 4, I want to plot the velocity magnitude. So here you can see in the X direction, and this is back of the truck. We have separation here and a very low amount of the velocity. So you have drag coefficient. If you wanna see what's the drag coefficient, just double click on this one and like edit the drag coefficient, press compute. You will see the amount of the drag coefficient. This is a minus value because negative value because the direction is the in opposite direction of the X direction, so we can define as a -1 and compute again, so it will give us the positive value. So we can calculate the lift force. So I will close this one, lift force, edit and compute. So we have the lift force again. We can it means that there's a press down instead of lift. So I will close this one and pause the video and open the post-processing. Now I have closed the Fluent and opened the post-processing. In the post-processing, I'm going to create a plane, XY plane, apply. So I'm gonna hide this plane, use that plane just as a location. So I will create a counter, and let's do the counter of velocity, 100, number of the counters, apply. Oh, the location is plane 1. I zoom in. You can see that we have the low velocity stagnation point at the front, and also very low velocity field at the back because of the separation. Also we can check the pressure. So let's see, local. So we have a high pressure point here, low pressure and lower pressure points here. Let's hide this counter. Let's do the streamlines. Surface streamlines instead of 3D on plane 1. Let's do 100 of them. So you can see that there's a separation and vortexes here. So we can also create some video. Go to slow, and let's hide these streamlines. No. Go to symbol, show symbol, apply. So the options, let's do 0.5, and we can see animate the streamlines. If you want to see the like how the fluid particles moving. So, or you can show the streamlines and show a symbol here. Let's do like 3D arrows, so you can see the symbol size, increase the size of the arrow or reduce it. Also you can hide this one and different type of streamlines. Let's do ribbon. Just the size of the ribbon. So this is the different ways of kind of working with the post-processing, but the main idea of this video to show how to calculate the drag force and drag coefficient and lift force. And thank you for watching. And please like and subscribe our channel and like our videos, and also if you have any question, please leave some comments for us. Thank you for watching.